morning. Today I'm going to talk about a relatively new aluminum nitride MEMS resonator technology, which is called aluminum nitride Cross-Sectional Lamé mode resonator. We call it CLMR, and we will experimentally show that the CRMR is capable of achieving 260 MHz frequency tuning range while preserving KT² higher than 4%. So I will briefly talk about the background motivation and then talk about the CRMR itself and its fabrication. Then we will show and discuss about the experiment result and conclusion. So let's look at this RF front and modular. Cellular signals of different frequencies will be received by the antenna. Then those signals will be sorted out by multiple duplexers. And we also have other kind of signals such as GPS or Wi-Fi, depending on the specific application. Those for one-way communication, filters can be just used to sort those signals out. But for two-way communications, usually we need a duplexers to accomplish this functionality. However, for duplexers, they are just basically a bunch of filters. Let's look at this picture. So a duplexer consists of two filters of different frequencies. The frequency response of a duplexer is also shown here. The one filter is used for outgoing signal, and the other is used for incoming signal. So the demand for more service bands is increasing all the time. In an advanced cellular system, up to 20 bands might be required. To give you a rough idea, here we are showing an example of carrier aggregation spectrum. So, since we need more channels, then we will need a lot of filters. And sometimes we also need wideband channels. As the bandwidth of filter is proportional to the KT² of the resonator, that means that sometimes we need a resonator with high KT². So it would be attractive if we can reduce the cost, volume, or even integrate those aluminum nitride, those filters on the same chip with our electronics. Here we are showing a proposed single chip RF modular based on aluminum nitride MEMS technology. In this figure, we are using contour mode resonators. Contour mode resonators can have the frequency tuning ability by lithography, and the resonators can also be used for building those local oscillators. Up to now, several aluminum nitride MEMS resonator technologies have been developed for replacing off-chip sort devices. The first one is F-bar, which has been used a lot in latest cell phones. The KT² can be as high as 7%. However, F-bar is using thickness extensional vibration mode. Thus, the frequency is mainly set by the thickness. Frequency tuning requires extra steps such as trimming or mass loading. Then CMR, the contour mode resonator, appeared as a promising candidate as it has the ability for tuning the frequency by just changing the pitch. However, the KT² is relatively low compared to the F-bar since it's using the E31 coefficient, which has lower amplitude than the E33. Then here comes the CLMR. CLMR is using a kind of mode which is called cross-sectional Lamé mode. The first order mode CLMR has the KT² of the first order CLMR has been found to be analytical found to be as high as 7%. A big advantage of that is we can still tune the frequency by lithography. However, there is a case similar to CMR. We do not want the first order CRMR as we need larger static capacitance to match to 50 ohm electronics. So in this work, we will talk mainly talk about 10th order CRMR fabricated, and as a consequence, there will be more lateral capacitance components in the CRMR, so the KT square will be reduced from 7% for the first order to about 5% for the 10th order. So let's take a closer look at the CRMR. In an intuitive way, you can think of CRMR as a resonator combining F bar and CMR. It's using vibrations in two directions. So thanks to the opposite sides of those two coefficients, it's possible to exist such a kind of cross-sectional Lamé mode. You can see from the displacement field of CMR, when there is a contraction in the thickness direction, there will be an extension in the lateral direction. And we are showing a 3D representation of our fabricated device. So it's similar to what we saw in CMR, but the main difference is that the thickness is comparable to the width pitch. We are also showing a cross-sectional view of CLMR to give you an idea how we apply the electric field to excite such a kind of mode. Other important parameters such as the finger number, which is 10, length 100 micron, thickness 4 micron, pitch 5 micron, and the metal coverage 60% is also shown here. For the fabrication, as we just saw, the structure is similar to CMR, so similar fabrication process can also be used here. First of all, the bottom electroplating deposition and patterning, then 4 micron aluminum nitride deposition, then we do the wet etch to form the vias, and we do the top electroplating deposition and patterning. Here we are using as the 4 micron aluminum nitride is relatively thick, so we are using a 2 micron silicon dioxide as a hard mask to etch the aluminum nitride. Then structural releasing. Here we are showing an SEM image of a 10-finger CRMR fabricated in this wall. From the parameters, you can see that this is exactly the same device as I just showed in the previous slide. The length, 100 micron, pitch, 5 micron, and the thickness is 4 micron. Okay, so let's go to the experiment result. As I just mentioned, the KT square is important for building filters with high bandwidth. Besides with the experiment data, we also put in a 3D simulation data from Coventer. There is a well agreement between the simulation and the experiment. Let's focus on the experiment data, which is marked as the red line and the red dots. So the highest KT square was found to be around pitch 6 micron, and this CRMR is believed to be the non-degenerate CRMR. Non-degenerate CRMR appears when the dimension satisfies strictly the cross-sectional Lamé mode condition, and it has the optimum pitch as well as the highest KT square. One interesting thing is that when the pitch is away from the optimum pitch, we can still tune the frequency without sacrificing the KT square too much. So to be clear, let's put the frequency and the KT square in the center. And the marked region here is showing the CLMRs which have the KT square larger than 4%. And so let's find the frequency range here. It's found to be about from 770 MHz to about 1.03 GHz, which is 260 MHz frequency range. And the other parameters are also shown here. The data is collected from fabricated 18 CRMR. We also measure the loaded collector and the resonance resistance. We defined this resonance resistance because we do not have this parameter is the resonance resistance is the sum of the series resistance and the motional resistance. We defined such a parameter as we do not have the capability to extract the series resistance due to the complexity we encountered during the real fabrication. So the dashed line and the dot marked as red is the loaded quality factor. It was found to have the highest loaded quality factor at the pitch of 4 micron. And consequently, as the motional resistance is inversely proportional to the quality factor, we also saw the minimum resonance resistance is found to be at the same pitch. The data is also from the 18 fabricated CRMR. Here we are showing the best CRMR we tested in this batch. So we have the measured admittance curve as well as the BVD fitting for this curve. And we also have the simulated curve here. We can also see well agreement here. And the KT square measured is found to be 4.3%, and the KT square simulated was found a little higher, about 4.5%. As the quality factor is about 1,600, we have figure of memory, which is the product of quality factor and the KT square, about larger than 18.5, which was the highest ever reported figure of memory for aluminum nitride MEMS resonator using IDT. Here is the main mode. You can see that the cross-sectional Lamé mode is mainly concentrated in the active region. And you must have noticed that there is a large spurious mode at the frequency around 950 MHz. And it was found to be a higher transverse Lam mode, and recently we found a way to suppress that. So here's the sample we just saw. And we have a lot of spurious mode here. And so we engineered the IDT finger, and we are able to suppress those spurious mode largely. It's also possible to suppress those spurious modes completely, but that will come at the cost of KT square. To give you an idea about the filter using this kind of resonator, we are showing a filter we just showed yesterday in the poster section. So that's from the simulation. We build the filter without the spurious mode suppression technique. Then we use the spurious mode suppression to engineer the active region, the IDT. Then we will have a very flat passband. So by doing that, we are able to get rid of most unwanted ripples in the passband. Okay, in conclusion, a high figure of memory in excess of 85 is reported in cross-sectional Lamé mode, and we are able to achieve 260 MHz frequency tuning range while preserving KT square larger than 4%. And with such a high KT square, it's able to build filter with fractional bandwidth about 3%. And we believe that will be a promising way to build integrated filters or duplexers. Okay, we would like to thank DARPA for supporting our work and UFFC for student travel support. Thanks.